Suppose R is a relation on a set A. Prove that R is transitive if and only if R composed with R is a subset of R. All right, well, why is that true? Let's draw a picture of sort of R composed with R. So we would need to write the set A 3 times, and we have an R here, another R here. All right, and then, okay, an element of R composed with R, well, that would be an ordered pair X, Z, such that there exists some ordered pair X, Y in R, and another ordered pair Y, Z in R, right? Okay, so the element there is the ordered pair X, Z, and we're saying that's in R too, so X, Z must also be in R. All right, that's exactly what it means for R to be transitive, right? If you take X, Y in R and Y, Z in R, then X, Z also has to be in R. Okay, so it's pretty believable. Let's think about how to prove it. R is a relation on A. That means R is a subset of A times A. And there's our if and only if statement. And if we want to prove that, we can just prove both directions. Okay. So we could use our proof techniques for each of those. We'll do that in a minute. But before we do that, let's try and prove this thing just with a chain of if and only if statements. So we will, maybe I'll back up a couple steps here. We're going to prove that one. All right. So start off with R is transitive, and we want to end up with R composed with R as a subset of R. All right, R is transitive. Definition of that is for all X in A, for all Y in A, for all Z in A, XRY and YRZ implies XRZ. And for the next step, all I'm doing is rewriting these sort of relation notation statements, XRY, in ordered pair form. So that means that the ordered pair XY is in R. And similarly for these other two statements. After that, I'm going to rewrite this conditional here as a not or, okay? And then let's think about where we're headed. Okay, R composed with R as being a subset of R means that, well, for every element of the left side is in the right side. Okay, so for all ordered pairs XZ, and this in A times A here is redundant. You don't really need that. XZ in the left side implies XZ in the right side. And working backwards from there, we see that XZ being in the composition means that there exists some Y sort of in the middle, right? Such that XY is in R and YZ is in R. And all right, so we're here and we're up there, and you see down here we have an existential quantifier. Up here it's a universal. And so to get from here to there, we should probably try and pull this negation symbol past the Y quantifier. All right. And all right, so, well, I guess before I do that, I'm going to take the for all X in A, for all Z in A, and just turn that into a for all ordered pairs X, Z, and A times A. Those are equivalent. And then I'll take this negation symbol and move it out past the universal quantifier so that it becomes an existential quantifier, which is applied to this conjunction here. And now I have a not this big statement or that one, and I can change that not or back into an if then, back into a conditional. All right, very good. And so this is where we got to. We already discussed that this here is the definition of XZ being an R times R. So we get here, and I probably should have also typed here if and only if R composed with R is a subset of R. Okay, so we got from the left side to the right side. Now let's go back and do it again using our proof techniques. So bring this back down. We're going to do these two directions. So for the first direction, we proved that R is transitive, that if R is transitive, then R composed with R is a subset of R. So suppose R is transitive for direct proof, and we're going to show that. And what's the first thing we would say? Well, to show this, we need to take sort of an arbitrary element of the left-hand side. So let's say let xz be an arbitrary element of R times R, and we will show that that element is in the right hand side, is in R. Okay. And so how are we going to do that? Well, we know xz is in R times R, so we know that there exists some y in A such that, and I can say I can say why not if I wanted, but I'll be a little bit sloppy and just go ahead and say y, okay, which is fine. So such that xy is in R and yz is in R. Okay. And then once I have those, I can say because R is transitive, which I supposed up here, it follows that, well, if xy is in R, yz is in R, and R is transitive, then I know that xz is in R, okay, which was my goal. So that finishes that direction, not too bad. Now let's think about the other direction. So next we prove that if R composed with R is a subset of R, then R is transitive. So suppose the first thing, we show the second thing. And how are we going to do that? Well, to show it's transitive, we're supposed to let x, y, and z all be arbitrary elements of A, such that we have what? X, y is in R, and yz is in R. And let me bring that down a line here. Good. And then we're going to show that xz is in R. xz is in R. Okay, so how do we do that? Well, we know that, okay, we have x, y in R and yz in R, so just like up above, that implies that, so we know that xz is in the composition of R with itself. Okay, and oops, we've supposed that R composed with R is a subset of R, so that means, okay, so because R composed with R is a subset of R, it follows that xz is in R as well, which is what we wanted. Okay, so we're done.